Welcome to today's deep dive. I am so glad you're joining us today because we are looking at something that feels, well, a lot like science fiction.
But it is actually science fact.
Exactly.
Yeah.
Our mission for this session is to explore a truly fascinating stack of sources. We are diving into the LH2 Era Blog archive.
Which is an incredible resource.
It really is.
Uh-huh.
These archives were written by Matt Moran. He's a NASA veteran with over 40 years of experience in power and propulsion.
Right.
And he is quite literally a pioneer in liquid hydrogen systems.
Yeah, and when you spend decades developing complex energy systems for things like the space shuttle or the International Space Station and cutting-edge terrestrial microgrids,
You see things a bit differently.
you really do. You develop a perspective that most of the general public they just do not have access to.
Right.
So the goal today is to bridge that gap for you. We are not just talking about another alternative fuel to put in a car.
No, not at all.
We are looking at a complete paradigm shift. How we handle our global energy grids, how we manage heavy transportation, and this is huge, how we might even address global water scarcity.
Which is just a massive claim.
It is, and the incredible thing is, we're going to explore all of this by looking at a technology that has secretly been powering our greatest human achievements for well over 6 decades.
Okay, let's unpack this. Because when we talk about the future of energy, you and I are so used to hearing the usual suspects, right?
Solar panels, wind turbines.
Exactly. And lithium-ion batteries.
Yeah,
But the author introduces us to this, he calls it an energy shapeshifter.
I love that term.
It's perfect because this is a system that doesn't just store power, it can actually create drinking water out of thin air.
Yep.
And if we are reading these sources correctly, out of things much grosser than air.
Considerably grosser, yes.
So I was looking at the system his former company, Isotherm Energy, designed. It's called the Hydrogen Energy and Renewables Architecture, or HI-URA.
Right, the high-URA system.
And as a non-engineer looking at the diagrams, the flow seems elegantly simple. But I want to make sure I'm getting this right.
Go for it.
So you take a renewable energy source, like a wind turbine, and you pair it with a water source.
Correct.
Then you use something called an electrolyzer to split that water apart. Can you just walk us through the actual mechanics of what is happening right there?
Yeah, I can certainly break that down.
Okay.
So an electrolyzer essentially uses the electrical current generated by your wind turbine or your solar panel to split the water molecule.
H2O.
Exactly. It splits it into its core elements, which are hydrogen gas and oxygen gas.
Okay.
The system then stores that hydrogen. And the beauty of this architecture is what happens later.
When the sun goes down.
Right. Whenever the sun goes down or the wind stops blowing, your renewable energy drops to zero.
Which is the big problem with renewables.
Exactly, the intermittency. But instead of the lights going out, the system takes that stored hydrogen and runs it through a fuel cell.
And a fuel cell does what exactly?
It does the exact opposite of the electrolyzer. It recombines the hydrogen with oxygen from the air.
Oh, wow.
Yeah, and that chemical reaction produces electricity to power the grid. And the only byproduct, literally the only exhaust, is pure, clean water.
So it acts as an incredibly effective buffer.
Yes. It addresses that fundamental flaw of renewable energy, the intermittency, completely cleanly.
But here is the detail from the source material that absolutely blew my mind.
The input water.
Yes. You do not need clean, purified municipal water to feed into that electrolyzer to make this work.
Not at all.
The sources say you can use salt water, you can use wastewater, you can even use urine.
Which is wild to think about.
I want you listening to this to just imagine setting up one of these microgrids in a remote developing region that lacks basic infrastructure.
Right.
If you use human waste as your initial input, the system runs through its cycle, and what you get out the other side is electricity, perfectly clean drinking water, oxygen, and nitrogen.
And that nitrogen can be directly used to fertilize local crops.
It's just unbelievable.
What's fascinating here is how this multi-output system completely changes the economic and environmental math of renewable energy.
How so?
Well, in a standard solar or wind setup, grid operators constantly battle a problem known as overgeneration or curtailment.
Let me stop you there. What exactly does curtailment mean in this context?
Think of the power grid like a highway.
Okay.
There is a speed limit, there's a maximum capacity it can handle safely at any given second.
Right, otherwise you get accidents, or in this case, blown transformers.
Exactly. So sometimes on a beautifully clear, windy day, the wind turbines spin too fast and the solar panels soak up too much sun.
They generate too much power.
They generate far more electricity than the local homes and businesses are actually using.
Wow.
And because the grid cannot handle that massive surge of excess power, operators actually have to shut the turbines down or disconnect the solar panels.
That seems like such a waste.
It is. That excess free, clean energy just gets wasted, curtailed.
Okay, I see.
The higher A architecture solves that by acting as a massive sponge.
Oh, because it uses the excess to make hydrogen.
Exactly. It takes all that excess electricity and uses it to split water, effectively storing that energy at a massive scale.
And hydrogen holds a lot of energy, right?
To put it in perspective, hydrogen can store 40,000 watt-hours per kilogram.
40,000. That is an astronomical density compared to the batteries sitting in our phones and laptops.
It is on a completely different level. And this leads to a major net energy analysis cited in the sources.
The one from Stanford.
Yes, conducted by researchers from Stanford University and Imperial College London.
Right.
They looked at various grid storage options to handle this overgeneration problem, and they found that a regenerative hydrogen fuel cell configuration actually provides a higher lifetime energy return on investment than the absolute best lithium-ion batteries available.
You know, I was actually confused by that part of the study.
The round-trip efficiency part?
Yes. Because the researchers mentioned that the round-trip efficiency of hydrogen is much lower than batteries. Can you explain what round-trip efficiency is and why hydrogen still wins out despite having a lower score?
It is a great question because it is where a lot of analysts get tripped up. Round-trip efficiency is basically a measurement of how much energy you get back out of a storage system compared to what you put into it.
Okay.
So if you put 100 units of electricity into a massive lithium-ion battery, you might get 80 or 90 units back out when you drain it.
That sounds highly efficient.
It is.
Hmm.
But if you put 100 units of electricity into making hydrogen, storing it, and running it back through a fuel cell, you only get about 30 units back.
You lose 70%.
You lose a lot of energy in the conversion process, yes.
Which sounds terrible on paper. Why would we want a system that loses 70% of the energy?
Because you have to look at the entire life cycle of the hardware, which is exactly what the Stanford researchers did.
Oh, I see.
Lithium-ion batteries degrade. Think about your smartphone. After 2 years, the battery barely holds a charge, right?
Oh, yeah. I'm lucky if it lasts till lunch.
Grid-scale batteries do the exact same thing. Plus, manufacturing those massive battery banks requires intense mining operations for lithium, cobalt, and rare earth metals.
Which is terrible for the environment.
You have to smelt those metals, build the battery, ship them across the ocean, and then, because they degrade, replace them every decade.
Wow, so the energy cost to just make the battery is huge.
Exactly. When you factor in the massive amount of energy it takes to build and maintain a battery farm versus what it gives back over its lifetime, the math shifts entirely.
Yeah, and hydrogen systems don't have that problem.
Hydrogen systems use basic elements like water, steel tanks, and electrolyzers. Those can operate for decades without degrading.
That makes total sense.
So when it comes to lifetime energy return on investment, hydrogen matches or beats batteries, even with that lower round-trip efficiency.
I really want to emphasize what this means for you. If you live in or care about regions of the world stricken by drought,
It's life-changing.
we are not just talking about keeping the lights on. We are talking about deploying a single system that secures reliable electricity, generates fresh drinking water out of wastewater, and produces crop fertilizer all at the exact same time.
It is the ultimate solution to the water-energy-food nexus.
But as beautiful as that vision is, I have to be honest. When I first looked at this stack of sources, I was skeptical.
Sure.
Because when average people hear the words liquid hydrogen, they immediately picture some far-off sci-fi concept. It feels like something we won't figure out for 50 years.
The author is highly aware of that perception, and the sources aggressively push back on the myth that this is an unproven fuel of the future.
It's not the future.
No. Liquid hydrogen, or LH2, has a deeply established space-age pedigree. It has been in continuous large-scale use for over 6 decades.
6 decades.
We are not waiting for a scientific breakthrough to make this work.
But 6 decades takes us back to the middle of the 20th century. How were they using liquid hydrogen back then?
The blog archive points out very specific historical examples. As far back as the 1950s, the military was conducting flight demonstrations with the Martin B-57 Camber aircraft running on liquid hydrogen.
In the 50s? That's incredible.
And that laid the groundwork for the space race. The Apollo-Saturn rocket upper stages, the actual vehicles that pushed astronauts out of Earth's orbit and toward the moon, relied on liquid hydrogen to get that massive thrust-to-weight ratio.
Of course.
The space shuttle's main engines burned it for 30 years. And today, modern operational rockets like NASA's Space Launch System, the United Launch Alliance Vulcan, and the European Ariane 6 all use liquid hydrogen.
So the aerospace sector solved the fundamental engineering challenges of this fuel a long time ago.
A very long time ago.
I love that you brought up the engineering challenges because I really want to understand the physics of the fuel itself.
It's fascinating physics.
I was reading through Moran's notes, and he kept talking about entering this thing called the cryozone. As a non-rocket scientist, what exactly happens to hydrogen when you get it that cold, and why is it necessary?
Well, you have to start by understanding how hydrogen behaves at normal room temperature.
Okay.
As a gas, it is incredibly light. It has a natural rise rate of 20 meters per second.
20 meters per second, that is what, 6 times faster than the natural gas we use in our stoves?
At least, which is actually a massive safety benefit, by the way.
Oh, because it doesn't stick around.
Right. If there is a leak, it doesn't pool on the ground and create an explosion hazard like gasoline fumes. It just rockets straight up into the upper atmosphere and dissipates.
That's a great point. But it also means it's hard to hold on to.
Exactly. Because it is so light and has such low density, trying to store enough of it as a gas to power a vehicle requires compressing it into incredibly heavy, thick-walled, high-pressure tanks.
Which you don't want on a plane or a truck.
No. So, to truly unlock its potential and store enough of it efficiently, you have to tame it. You have to enter the cryozone.
The cryozone.
By chilling hydrogen gas down to its normal boiling point, which is a freezing negative 253 degrees Celsius.
That is unbelievably cold.
It is. But when you do that, it undergoes a phase change. It becomes a liquid.
And when it becomes a liquid, the volume shrinks dramatically, right?
Precisely. You vastly increase its volumetric density. You can pack a tremendous amount of energy into a much smaller space, and because it is a liquid, you no longer need those extreme, heavy, high-pressure storage tanks.
You just need insulated ones.
You just need very well-insulated tanks.
Here's where it gets really interesting. We are watching this space-age tech come down to Earth to completely decarbonize the sectors that standard batteries just cannot handle.
The heavy lifters?
I am talking about the heavy lifters of our global economy. Long-haul trucking, maritime shipping, and transcontinental aviation.
If we connect this to the bigger picture, the reason batteries fail in those sectors comes down to a concept the blog calls the weight versus volume tug-of-war.
Break that down for us.
Let's compare the physical properties of liquid hydrogen to fossil fuels. By mass, which engineers refer to as gravimetric density, liquid hydrogen is a powerhouse.
Right.
It packs nearly 3 times the energy of your standard jet fuel or diesel. It is incredibly light for the punch it packs.
But there's a catch.
But by volume, it is very fluffy. A gallon of liquid hydrogen holds less than 25% of the energy content of a gallon of gasoline.
Let me make sure I am visualizing this. So if I have a pound of liquid hydrogen, it will give me 3 times more energy than a pound of diesel.
Yes.
But if I want to match the energy of a 1-gallon milk jug full of diesel, I would need 4 milk jugs full of liquid hydrogen.
That is the perfect analogy. It weighs almost nothing, but it takes up a lot of space. And that unique physical profile is exactly why liquid hydrogen is considered the holy grail for heavy logistics. In the world of commercial trucking and passenger aviation, weight is the absolute enemy.
Weight equals lost revenue.
Always.
Right, because a truck can only legally weigh so much on the highway. And an airplane can only generate so much lift.
Exactly.
Every kilogram you add to the vehicle itself is a kilogram you can't use for paying passengers or profitable cargo.
Which is the fatal flaw of trying to electrify heavy transport with batteries.
Because they're so heavy.
If you try to power a transcontinental cargo plane or a long-haul semi-truck with heavy lithium-ion batteries, every kilogram of that massive battery pack eats directly into your payload.
You'd end up carrying nothing but batteries.
Eventually, yes, the vehicle becomes so heavy it can barely carry anything but its own massive battery. It is economically useless.
But liquid hydrogen fixes that.
Because liquid hydrogen is so remarkably light, these vehicles can maintain their massive payload capacities while also achieving incredibly long ranges.
But because of the volume issue you mentioned, the 4 milk jugs instead of 1, the fuel tanks have to be physically larger.
Yes, they do.
You might have to stretch the fuselage of an airplane or design entirely new, slightly bulkier tank packaging behind the cab of a semi-truck.
Right.
But the author's point is that the economic trade-off heavily favors liquid hydrogen for these big applications. The math works because keeping the cargo weight high is more profitable than keeping the truck slim.
The physics of the fuel directly drive the economic viability. You redesign the shape of the plane, but you get to keep all the seats.
Okay, but let's play devil's advocate for a second, because I know what you're probably thinking listening to this.
The boil-off issue.
Yes, if we have to keep this fuel chilled to negative 253 degrees Celsius, isn't it just going to boil away the second a truck sits in traffic on a hot day, or a plane waits on a tarmac in July?
It's a fair question.
How do you store something that cold without losing half your fuel to evaporation?
It is the most common critique you hear from skeptics, but the source material offers a firm reality check based on direct engineering experience.
Because Moran has built these.
This isn't theoretical. Matt Moran himself has designed zero boil-off liquid hydrogen tanks.
Yeah.
And we are not talking about small, high-tech thermoses here. We are talking about massive infrastructure.
How massive?
He has designed tanks as large as 4,732 cubic meters, with absolutely zero loss.
How is that physically possible? Even the best insulation in the world eventually lets heat leak in.
You are correct. Insulation alone only slows down the heat. To achieve zero boil-off, you use a combination of advanced vacuum-jacketed insulation and active cryo-refrigeration.
Oh, active refrigeration.
Essentially, you integrate a highly efficient closed-loop chilling system right into the tank.
Okay.
If a tiny amount of heat does penetrate the insulation and causes a wisp of liquid hydrogen to vaporize, the active refrigeration system captures that gas, chills it back down to negative 253 degrees, and turns it right back into a liquid, dropping it back into the pool.
It catches it before it can escape.
The fuel never escapes. You can hold liquid hydrogen indefinitely without losing a single drop to boil off.
That is staggering. A massive storage tank with zero loss completely changes the narrative.
It does.
And it leads into another massive blind spot that the archive points out regarding current economic reports.
The pipeline assumption.
Right. A lot of financial analysts look at the hydrogen economy and assume the fuel is going to be incredibly expensive.
Yeah.
And they assume that because they think we have to pipe it across the country, just like we do with oil pipelines and natural gas infrastructure.
They bake these huge transportation, pipeline construction, and distribution losses into their economic models.
Which completely ignores the new infrastructure paradigm that liquid hydrogen enables.
Yeah.
Point-of-use generation.
Exactly. Because hydrogen can be made from just water and electricity, you do not have to drill for it in a desert, load it onto an ocean tanker, and pipe it 1,000 miles to a refinery.
You can just make it where you need it.
Yeah.
Imagine you're looking at a major international airport. Instead of relying on vulnerable pipelines piping in thousands of gallons of jet fuel every day, the airport simply builds its own dedicated solar microgrid and a modular liquefier right there on the unused land around the runways.
They take local water, use the sun to split it, chill it into liquid hydrogen, and store it in those zero boil-off tanks right on the tarmac where the planes fuel up.
There are zero distribution losses, zero pipeline costs, and zero shipping emissions because the fuel literally never leaves the zip code it was manufactured in.
This point-of-use paradigm is an absolute game changer. Producing, storing, and delivering the fuel all in the exact same footprint fundamentally rewrites every assumption and cost analysis that skeptics use to dismiss the technology.
It's brilliant.
It makes the entire supply chain incredibly resilient to global shocks.
And what I find so inspiring about Moran Innovation is that they are not hoarding this specialized knowledge behind expensive corporate paywalls.
No, they're giving it away.
They are actively democratizing the aerospace engineering required to build these point-of-use systems. The blog mentions they have released open-source software tools into the public domain.
Like CryoFM.
Right. There's a tool called CryoFM, which uses Python and Jupyter notebooks, and another tool called LH2 Sage. They are giving engineers, researchers, and students around the globe the complex thermodynamic modeling tools they need to design these exact systems for their own local communities.
The motivation behind giving away such valuable intellectual property ties back to an aggressive industry target known as the 1-1-1 goal.
1-1-1. What does that stand for?
That stands for producing 1 kilogram of clean hydrogen for $1 in 1 decade.
1 kilogram, $1, 1 decade.
Hitting that price point is what makes liquid hydrogen cheaper than fossil fuels. By putting high-level aerospace engineering tools into the public domain, they are empowering local engineers everywhere to optimize supply chains, experiment with tank designs, and innovate faster. They are crowdsourcing the path to hitting that critical economic tipping point.
So what does this all mean for you listening right now? We are actively entering a phase of human history where the heavy lifters of our world, the massive container ships bringing goods across the ocean, the fleets of trucks delivering your packages, the transcontinental planes you take on vacation, can run on a zero-carbon, space-proven fuel.
And the only exhaust they will leave behind in the atmosphere is a crystalline mist of pure water.
I really want you to take a second and imagine what silent, soot-free skies and unpolluted shipping lanes will mean for your daily life, the health of your community, and the stabilization of our climate.
It is an incredibly hopeful vision of the very near future.
It really is.
But before we wrap up today's session, there is one final, truly mind-bending concept tucked into the text that I want to leave you with to ponder.
Oh, lay on us.
For this entire deep dive, we have talked exclusively about manufacturing hydrogen, taking water, applying renewable electricity, and splitting it apart to create a fuel.
Right, making it from scratch, essentially.
But what if we didn't have to manufacture it at all? What if we could just mine it like we do natural gas?
Wait, mine it. I thought hydrogen was too light to exist naturally on Earth without bonding to something else.
That was the conventional wisdom for a long time. But the author briefly points to the emerging scientific prospect of geologic hydrogen.
Geologic hydrogen.
Geologists are discovering that naturally occurring hydrogen gas is constantly being created by subterranean catalytic reactions in iron-rich rock formations deep within the Earth's crust.
You're kidding.
No, it is a natural geological process separating the hydrogen from groundwater.
Wow.
This raises an incredible paradigm-shattering prospect. Could the next great global energy rush look exactly like the oil booms of the past century?
Only this time, instead of drilling for toxic, carbon-heavy crude oil, we are tapping into massive reservoirs of a completely clean, naturally replenishing gas right beneath our feet.
Talk about a cliffhanger. A green gold rush happening right beneath our feet, constantly refilling itself. Thank you so much for joining us on this deep dive into the LH2 Era archive. We hope this exploration empowers you to keep questioning the assumptions you hear about energy, to look past the usual suspects, and keeps you immensely curious about the incredible technologies shaping our future. Until next time.